Alright guys, welcome to Code Off. Today we are going to look on recursion. So this is a recursion series, and actually I wanted to start with the dynamic programming series, but I thought maybe recursion is the base of the dynamic programming. You will build the DP solution if only and if you know the recursion. Okay, so what this in this series what we are going to do is first I will like to introduce some concepts in recursion. I will show how to find a recursive solution, and I will also be listing out some problems, like some beginner friendly problems, some intermediate problems, and some advanced problems to get a good grasp in recursion. So make sure you follow the whole series, because if you miss any point, then when I start the DP series, you might not be able to grasp the solution for that DP problem. So make sure you follow the whole recursion series. Okay, so let's get started. In this recursion series, today we are going to, in part 1, we are going to look in some these 5 steps. Okay, so let's see. Okay, so what are the 5 steps? First, we will define what is recursion. We will then check how to find the recursion solution. Then we will go step by step to get into that recursive function, and then we will see what is the tail recursion, and then we are going to see an important concept like why quicksort is faster than merge sort. Why do we use quicksort in CPP functions? So in every sort functions actually. So let's get started. First, what is recursion? Now you might be wondering why do we need recursion? So the main point of recursion is we want to break down big problems. Like if we want to find any big integer, and we know some small integer values. Let's suppose we want to find a factorial, and we know that the factorial of 1 is 1, but we want to know what's the factorial of 100. So what we do is we break down that factorial number into smaller numbers, and we go until we have our base condition. So let's say we want to find any recursive function. Then what we do is we break down the whole problems into smaller chunks, and we go until we reach to a base condition. Now what's the base condition? You might be wondering why do we require a base condition? Well, if we don't have a base condition, then there is a high probability that you will run into a memory overflow. So we want to avoid that. So what happens is, let's suppose a base condition is defined like, let's suppose you want to go from the 3rd floor to a particular shop. Now you will not go to a particular shop by just flying. You will go there to second floor, then 1st floor, then ground floor, then go to the shop. So what's our base here? Our base is the ground floor, right? So what we want is our base condition to be defined. If we don't have ground floor, then it's like going underground. So it's more of a the most important thing in recursion is the base condition. Now as you can see, if we don't have a base condition, then we will run into a memory overflow. As you can see, we will never get out of the function. So we will just go inside the function, and it will run the loop for infinite number of times. Now let's see an example. Let's suppose we want to calculate the factorial of a number. Now here I have defined Fibonacci number. So the mistake I have done that Fibonacci number, but this is a factorial of a number function. Now how we calculate a factorial of a number? Let's define the iterative approach. Okay, so what we do is we start from the n-1, which is the we set our I is equal to n-1. We go until we reach 1, and we multiply. Like let's suppose we want to calculate the factorial of 5. We start with 5, and then we multiply it with the n-1, then n-2, n-3. That is 5 into 4 into 3 into 2 into 1. That is until we reach 1. So that's way we calculate the factorial of a number. But in this example, iterative approach might be better than the recursive approach. But there are many problems where recursive functions are very much important than the iterative approach. So we need to find that recursive function. Now how are we going to find the recursive function? We will go step by step. How should we find the recursive solution? Number one, we need to define our base condition. As I stated before, if we don't have a base condition, then we are never going to return from our function. We will be inside the loop always. So we need to define our base condition. Now how do we usually calculate the factorial of a number? We say that fact phi is phi into 4 into 3 into 2 into 1. Fact 3 is 3 into 2 into 1. Now is there any common thing you notice here? Yep, there is. What's the common thing you see in the above examples? That is 1. So that means whenever we calculate a factorial of a number, we run into some common thing, that is some base, which will always lead to the termination of the program. So, and that common thing here is 1. So we define our base condition as 1. Now you might be wondering, why not 2, right? Why can't we use 2 then? We want to so what happens if we want to calculate the factorial of 1 or maybe 0? So 2 is not the correct base condition for this function. So we need to define as base as possible, such that every integer, every natural number we are approaching, it should satisfy the condition. So we will go with the 1 as our base condition. That is why we are going to set our base condition as 1. Now let's step 2. What's the most important thing whenever you approach to a recursive solution? That is recursion tree. It is the very much important it's the most important thing whenever you find a recursive solution. You need to draw a tree. Now many of these students, what they do is they just think like they will get the solution by just thinking, without if they have not done any practice. So most of the time you will not get the solution until you draw a recursion tree. Now what's a recursion tree, you might be asking? So recursion tree is something like this. What you do is you set a function, then you define that function, means you define a function and you go until your base condition is satisfied. Like let's say we want to calculate the factorial of phi. What we do is our relation is now n into n minus 1, right? So where will our n minus 1 go? It will go into our factorial function. So what we do is n into factorial of n minus 1. Now here, when we call the factorial phi, this function will always be in a pause state. It will never resume until we reach our base condition. Remember this. It will only resume when we reach our base condition. So let's start. Factorial of phi. Phi into factorial of n minus 1, which is factorial of 4. Now this is also in a pause state. It is not also resume until we reach factorial of 1. Then again we call this function. Now it will return 4 into factorial of 3. It is now factorial of 3 is also in pause state, so 3 into factorial of 2. Factorial of 2 is also in pause state, so 2 into factorial of 1. Then we reach factorial of 1, which is our base condition, right? So if we reach 1, what's our base condition? We will return the answer as 1. So when we reach factorial of 1, we will reach our base condition and we will return 1 to the answer. Now what's the now here this function will resume its state and it will give 2 to the above function, which is factorial of 2. So now factorial of 2 gets 2 as the answer. So now 3 into 2 is 6. Now 6 will give its answer to its parent function, which is factorial of 3. So what is now 4 into 6, which is 24, and 24 will give its answer to the factorial of 4, that is its parent function. So now 24, so 5 into 24 is 120, and this 120 will give its answer to its parent function, which is factorial of 5. So as you can notice, we start from the bigger problem, we break down the problem into smaller chunks, and then we try to build this problem from the smaller chunks into our bigger solution, which is factorial of 5. So recursion tree is very much important when you define a recursive solution. So make sure whenever you practice a recursive function, you always draw a recursion tree. Step 3, finding the relation. Now in this state, what we did is we find this relation, that is n into n minus 1, correct? So but how come this relation will come? See, this is finding the relation is like means you need to get into that state where you will tell a particular problem to break down into chunks, right? So you need to divide those chunks. So what is our relation in the factorial of a number? This is this is like some of the hardest part of the recursive function. As you can see from our recursion diagram, we need to we start from the nth number, we reduce the number by 1, then go until we reach 1. That is, we start from n, then we multiply it with by n minus 1, then multiply it with by n minus 2, then n minus 3, until we reach our factorial of 1. So our relation in this state is n into n minus 1. So defining a relation is very much important when it comes to recursion. So there are 3 steps. First is you need to define your base condition. Second is you need to draw a recursion tree, like at least draw a tree until you reach to a point where you notice that yes, this is overlapping, this thing is this, until you reach to a particular point where you understand the whole function. So draw recursion tree, next find the relation, and at last start creating the function. So yeah, what we have done, we created our base condition, we draw our and we stated our relation, recursive relation, and this is the function. We say fact of int of n. We define our base condition as n is equal to 1 or n is equal to 0, because 0 factorial is also 1. So whenever we reach this base condition, we will return 1, and until we reach this base condition, we will return n into fact of n minus 1. That is n into fact of 4, then fact of 3, fact of 2, and fact of 1. So that's how this recursive function works. Now let's start. This is the last part of this part 1, and which is tail recursion. Now you might be wondering, what is tail recursion? You must have conquered this very much frequently. Like, let's say a tail recursion, when we define our recursive relation at the end of our function, and after that recursive relation there is nothing, like there is no print statement, there is no variable declaration, nothing. So when we define our recursive relation at the end of the function, we say that this is our tail recursive function. Now let's get into some of the examples. Now this is a non-tail recursive function because there is a print statement at the end after the function. So how this function works, we start from n, we say call the recursive function, we say n minus 1. That means, let's say I have called phi, so phi will be its parent function, then this function will call, so it will be 4, then it will be 3, 2, and when it reaches 1 it will return. So when it reaches 1 it will print the n, that is 2, then after that it will give it to the parent and it will say 3, 4, 5. So that's how non-tail recursive function works. That means there is something after the recursive relation, there is something after the function which we have defined. And example of tail recursive function. So a tail recursion function means that there is nothing after the tail recursion function. So what we do is we print n before the tail recursion function. So let's say I want what's 5, so we print 5, then we run the function again, then we print 4, then 3, then 2, and after that as we reach 1 we just return. That's it. This is the tail recursion function. So, and there is like very much like a common usage of tail recursion and non-tail recursion function in our programming. And what's that? Well, you know Quicksort. Quicksort is the function which is used in our sorting algorithms, which are like CPP sorting functions. So Quicksort is used. Why not merge sort? Well, merge sort is slower than Quicksort. It is because that merge sort is is having a non-tail recursion function. That means when we divide our array into merges, and after dividing whole array, what we do is we again check those arrays. So that means after the function there is also another statement after the function. That's why it's not a tail recursion function. So yeah, merge sort, there is no tail recursion function. That's why it is slow. Again, this is a typo mistake. Merge sort is a non-tail recursion function. I have by mistakenly like typed here, and in Quicksort there is a tail recursive function. So again, this is by mistake, it's a typo, so sorry for that. But Quicksort is having tail recursion function. That's why tail recursion functions are faster than the non-tail recursion function. Now this is there is a typo mistake, so make sure you I will state that in the comment section that Quicksort is a tail recursion function and merge sort is a non-tail recursion function. So that is why Quicksort is faster than merge sort. That's it guys, this was the end of the part 1 recursion series. Hope you guys liked it, and this series will continue, and I will list all the beginner friendly problems, intermediate problems, advanced problems in the further series. Make sure you follow the whole series, because if you don't follow, like if you cut between the videos, then you will not get you will not grasp that recursion part whole. So make sure you follow the whole series, and like, share and subscribe guys. Cheers.